In Chapter 6, Section 2, we discussed conservation of momentum. A collision occurring between two objects in a closed system conserves momentum. When they collide, they both experience action-reaction pair of forces, so they each experience the same force for the same time. So the impulse momentum theorem told us that a force times a time equals a change in momentum. So what one object gains in momentum, the other one loses the same amount. So in other words, the total momentum doesn't change. And that's what we said. The initial momentum, P sub I, is equal to the final momentum, P sub F. And if we replace the momentum before the collision with the sum of the momenta of each object, that would be the mass of object 1 times the initial velocity of object 1. And the same for object 2. So m1 v1 initial plus m2 v2 initial is my initial momentum. That will be the same as m1 v1 final plus m2 v2 final. And that was the law of the conservation of momentum. It might also be possible that kinetic energy is conserved as well. And if that is the case, we would say the initial kinetic energy before the collision is equal to the final kinetic energy after the collision, and we would quantify that as 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared for the kinetic energy before the collision equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. In everyday collisions of common objects, kinetic energy is not conserved because energy is transferred to other forms, such as sound and heat. We give these two different types of collisions names. If kinetic energy is conserved, we call that collision an elastic collision, and if it is not conserved, we call it an inelastic collision. Notice that in both types of collisions, momentum is always conserved. However, the elastic collision, by definition, is one in which kinetic energy is conserved, and all other types of collisions where kinetic energy is not conserved, we call it inelastic. I mentioned here, everyday collisions, kinetic energy is not conserved. So that means all the collisions that we're used to seeing every day, anywhere we go and anything we do, those are examples of inelastic collisions. So let's look at some examples of inelastic collisions first, and then we will show you where we can observe elastic collisions. Our first example of an inelastic collision will be a head-on collision of two cars. The most dangerous type of collision between two cars is the head-on collision. During the collision, the two cars form a closed system. Let's make the reasonable assumption that during the collision, the impulse between the cars is so great that we can neglect the relatively minor impulses due to the frictional forces on the tires from the road. Then we can assume that there is no net external force on the two-car system. Let's watch the collision. Both cars had kinetic energy before the collision. Neither car has kinetic energy after the collision. So kinetic energy is definitely not conserved. However, momentum is a vector. The momentum of one car in one direction was equal and opposite to the momentum of the other car in the other direction. So their net momentum is 0 both before and after the collision. Momentum is conserved in an inelastic collision. Let's look at an inelastic collision between a ball and a floor. How do I know the collision is inelastic? Well, you notice that each time the ball bounces, it does not bounce to its original height. If kinetic energy was conserved, the ball would leave the floor at the same speed at which it came in, and it would go to the same original height. But since that doesn't happen, I know some of the energy is being lost to sound, and also some of the energy is heating up the ball and heating up the floor to a small amount. Is the ball really heating up? Yes. Let's look at another example that confirms that the objects are increasing their thermal energy.
Oh, hi, I'm Dr. Baseball, Einstein of the national pastime. Hey, I'm studying the thermal energy created when the ball hits the table. The ball doesn't go back to the height from which it was dropped because the collision creates thermal energy. You know, this would be a lot easier if you could just see the thermal energy. And it'd be a lot more fun if it happened in a real baseball game. Well, in 2011, Fox Sports used a thermal imaging camera during the World Series. In this image, you can see the warmer objects, like the player's bare arms, are whiter than the cooler objects like the ball, which is almost black. Check out this crucial play in the top of the 9th inning.
Trek. That's a foul ball. Now they're not saying foul ball. Out.
Well, what was it? Did it hit the batter's toe and it's just a foul ball? Or was it a weak dribbler to third base for an out? Let's look at the thermal image of this play and then we can see what it was.
Let's take another look and see if there's anything that lights up, and right off the tip of the shoe.
Right off the toes.
That ball nicked him. But it's out number 2.
That's right.
Did you see the ball and bat turn white from the thermal energy in the collision? Did you see the white spot on the batter's toe from the collision there? Well, let's look at the video one more time. Watch the ball turn white as it hits the bat. See the white spot on the batter's toe? It was just a foul, not an out. Since you probably don't have a thermal imaging camera, why don't you try these colliding steel spheres from Arbor Scientific? Smells like something's burning. That reminds me of Ted Williams. He was the greatest hitter in the history of baseball, and he claimed that when he fouled a ball back, he could smell burning wood. Well, after doing this experiment, I'm inclined to believe him.
So if all collisions that we can observe create sound and heat, how is there such a thing as an elastic collision where kinetic energy is conserved? Because for kinetic energy to be conserved, no energy can change to sound or heat. Well, here is an example. If you take a look at this animation, this is an animation of molecules vibrating on the atomic scale. Heat, if you think about what heat is the vibration of molecules, and sound is the vibration of molecules. So if we only have 2 atoms or 2 molecules colliding, how can heat or sound be generated? The answer is they're not. Collisions between atoms and molecules are elastic. However, there are some macroscopic collisions that can come close to being elastic. We can approximate those collisions to be elastic and treat them as elastic collisions, even though a small amount of energy is transferring to other forms. Here's an example of an approximated elastic collision. There is sound being generated, and we know from watching the video that when steel balls collide, some heat is also generated, but in this case, the amount of sound and heat is so small that the kinetic energy really doesn't change very much at all. You can tell this because the balls continue to bounce against each other for a very long time, indicating that the kinetic energy is changing to other forms at a very slow rate. A very small amount of energy is lost in each collision. So therefore, we can approximate this collision to being very close to elastic. The inelastic collision of 2 bodies always involves a loss in the kinetic energy of the system. The greatest loss occurs if the bodies stick together, in which case the collision is called a completely inelastic collision, in this case between a defensive end and a quarterback. The colliding objects stick together and move as one after the collision. Let's add this now to our slide of definitions of collisions. Now we have the elastic collision, the inelastic collision, and the completely inelastic collision, where the colliding objects stick together and the loss of kinetic energy is the greatest. Momentum is still conserved. So if we have the inelastic collision and the completely inelastic collision, that means there are varying degrees to which a collision is inelastic. Let's see how these varying degrees affect the impulse or the change in momentum of an object after a collision. In our first example, we'll look at bouncing occurring. So if an object comes in and bounces off something, its incoming velocity, we'll let the incoming direction be the negative direction. Let's just use as an example an incoming velocity of 3 meters per second, and it bounces off at 2 meters per second. This is a change in velocity of the final minus the initial, or 2 minus negative 3, a change in velocity of 5 meters per second. Then if no bouncing occurs, such as in a completely inelastic collision, we see that our final velocity now is going to be 0. And so our delta velocity is only 3 meters per second. It is less. The change in velocity is less when no bouncing occurs than when bouncing does occur. So up here, if this number is larger, that means our impulse is larger. Our change in momentum is larger. And let's see how this can affect an object.
I have a super ball and a koosh ball. And to show that they're the same mass, I'm going to hang them over a meter stick and use the meter stick as a balance to show that they have the same mass. Hang them over either side and put my finger right in the middle, and you see that it balances, showing that they have equal mass. Okay, so both the koosh ball and the super ball have the same mass. The super ball, of course, will bounce off the block. The koosh ball will not. I will release them from the same height, which the string will be parallel to the floor to let you know they're being released from the same height, and we'll strike the block. Okay, no bouncing. Bouncing.
Wow.
So a greater impulse with the bouncing as opposed to the not bouncing.
This is a 2.5-inch steel ball dropped on cement at 12 inches. This is a 2.5-inch steel ball dropped at 12 inches.
If you've seen the movie Shrek, you're probably familiar with this scene. Shrek has just saved Fiona from the dragon and is taking her back to the land of Duloc to Lord Farquaad when, while passing through the forest, Robin Hood comes upon them and decides he needs to save Fiona from the ogre. And this is the scene where he tries to steal her away from Shrek.
Princess!
So Robin Hood swept Fiona up with a completely inelastic collision. Remember, that means that as they collide, they move together after the collision as one object. Let's simulate this situation in the lab.
We're going to simulate the Robin Hood Fiona situation with these two tennis balls that I've covered with Velcro so that they stick together. This ball will represent Fiona standing on the floor of the forest, and this ball will represent Robin Hood, who will come swooping down out of the tree, pick up Fiona, and then they will rise together as one object to a new height up in the tree. Let's assume that Robin Hood and Fiona have about the same mass, so each ball represents each person, each of mass m. I'm going to release Robin Hood from a height of 80 centimeters and pause the video here and try and figure out and predict how high the two of them will rise after the collision. Will it be 40 centimeters or 1/2 the original height? 20 centimeters, 1/4 the original height? or 10 centimeters, 1/8 the original height. I'll give you a hint. Break it down into 3 parts. The first part is the transfer of Robin Hood's potential energy to kinetic energy. Then the second part is the collision, the conservation of momentum during the collision. And then the third part, the velocity after the collision, translates to a kinetic energy, which will then change to potential energy as the two rise together to a new final height. Pause the video here and try and figure it out, and then come back and see if you're right. We'll perform the experiment, and you can see if you correctly predicted the final height. Okay, here we go. "20 centimeters, 1/4 the original height." Let's look at the calculations.
So here's our situation. We start here with potential energy mgh1, where h1 is the height before Robin Hood swings down out of the trees. Then Robin Hood's potential energy, gravitational potential energy, converts to kinetic energy due to conservation of mechanical energy. So that is step 1 of the problem. And we see here that the potential energy mgh1 is the same as the kinetic energy just before the collision, where v1 is the velocity of Robin Hood just before he scoops up Fiona. And solving that for v1, I get the square root of 2gh1. Then in part 2 of my solution, during the collision, momentum is conserved. So prior to the collision, the momentum is entirely with Robin Hood. So mv1, Robin Hood's mass times his velocity, and that is the same as the momentum after the collision, mv, where the mass is 2m now, Robin Hood plus Fiona, and their new velocity, v2, the velocity right after the collision. So it makes sense, if momentum is conserved, if the mass doubles, the velocity cuts in half. And that's what we see. Our new velocity, v2, after the collision is 1/2 the velocity before the collision. Then in part 3, the kinetic energy associated with their new velocity, v2, converts to potential energy as they rise up into the trees, and all of their kinetic energy down here converts to potential energy up here, which is mgh, but the mass is now 2m, and the height is our new height, h2. So that's what I've written here. 1/2 mv squared is the kinetic energy right after the collision. 2m is the mass. v2 is the new velocity. Equals mgh potential energy at the top of the swing, where m is 2m and the height is h2. The 2m's cross off from either side. The 1/2 cross multiplies over to the right to become a 2. And now I'm going to substitute for v2 what I got here, v1 over 2. And then I'm going to substitute in for v1 what I got up in part 1, that it's the square root of 2gh1. And when I do the algebra here and solve for h2, I see that h2 is 1/4 of h1. And that's what we saw. The two tennis balls rose to a height of 20 centimeters, which is 1/4 of the starting height of 80 centimeters. So I'll leave it to you to decide if this is a realistic depiction of what could really happen. In all this talk of collisions, whether they be elastic or inelastic, let's remember one very important idea. And that is that in a closed system in which no mass or energy enters or leaves, momentum is conserved. We can justify this statement by looking at the action-reaction pair of forces between colliding objects. When object 1 collides with object 2, 1 exerts a force on 2, and the reaction to that is 2 exerts a force on 1. Forces are equal in magnitude, but opposite in direction. And the time of the collision is the same for both objects. So therefore, looking at the impulse momentum theorem, if both objects experience the same force for the same amount of time, they'll both experience the same change in momentum. The change in momentum of the first object will be equal but opposite in direction to the change in momentum of the second object, so the net change then is zero. And that's what we say here. Momentum is conserved. That means the net change in momentum is zero. Now let's look at elastic collisions in one dimension. Remember that elastic collision is one in which kinetic energy is conserved. So that means the initial kinetic energy before the collision is the same as the final kinetic energy after the collision. And here is the equation that would allow us to figure out those values. Remember, momentum is conserved in all collisions. Here we're going to analyze an elastic collision between a moving ball and a stationary ball. We'll call the incoming ball the projectile, and we'll call the stationary ball the target. So the target is going to be struck by the projectile. And if we look at our equations over here for conservation of kinetic energy and conservation of momentum, they look quite long. But if we have a stationary target, then the equations simplify somewhat because V2 initial is zero. So you see on the left-hand side of the equations, the terms that had V2 initial in them disappear because V2 initial has a value of 0 meters per second. Because it's an elastic collision, kinetic energy is going to be conserved, and all collisions, momentum is conserved. So here's our equation that shows our conservation of momentum, and here's our equation that shows our conservation of kinetic energy. An air track is very similar to an air hockey table. It has many, many holes that air is pushed out by a fan. So here we see the fan, and the operator has just turned the airflow up, and these gliders are like the pucks on an air hockey table, and they slide with very low friction, and we can now have our collision. Here is an example of an elastic collision. We see that one cart completely stopped and the other cart moved on with the same velocity, conserving kinetic energy. Now we've made one cart heavier than the other. And let's try a sample with numbers. So let's do an example problem here, and we'll do it with numbers. So this projectile cart is coming in with a mass of 500 grams or 0.5 kilograms
At a speed of 3 meters per second.
and it's going to collide elastically with a second cart that has some weight added, so it's heavier. Its mass is 1.5 kilograms, but initially it's at rest. So we'll start with our equation for conservation of kinetic energy that says the kinetic energy of the first cart initially plus the kinetic energy of the second cart initially together is the same as the total kinetic energy of both carts after the collision. So we know that our equation for kinetic energy is 1/2 mv squared. So I filled in all the 1/2 mv squareds with the proper subscripts. And the second cart initially is at rest. So this term is 0. So that's this 0 here. And my unknowns in the equation are the final velocities of the first cart and the second cart. So I'll simplify the equation down to this step, and I see that I have two unknowns, V1 final and V2 final. I need another equation to solve this because I have two unknowns. And I will get that other equation from conservation of momentum. So the momentum of the first cart, the momentum of the second cart, initially together is the total momentum of the system, and that will remain unchanged. It is the same as the momentum of the two carts added together after the collision. So I go ahead and plug in the numbers that I'm given for a mass and velocity, and I can simplify it to solve for V1F in terms of V2F or V2F in terms of V1F, and then I can take my pick and substitute one of these back into the equation I got for kinetic energy. Of course, we're just solving a system of equations here, two equations with two unknowns. And here we go. I chose to plug in my expression for V1F here. So that's what I did. My V1F expression is plugged in there. And now I simplify that and solve for V2F, and I see that it's 1.5 meters per second in the positive direction. And then when I plug that into my equation to get V1F right here, I see that my first cart is going to be moving backwards, negative 1.5 meters per second. And let's look at the video again and confirm to see that yes, in fact, the second cart moves forward and the first cart moves backwards.